Today we're going to start talking about the normal distribution. So the normal distribution is probably the most important probability distribution we're going to talk about because we're going to use the normal distribution in everything that we do from this point onward in the rest of the class. So the normal distribution is a continuous random variable. So remember what that means. It means that it has an infinite number of possible values that can be represented by some interval on the number line, right? So an example of a continuous random variable would be something like the hours spent studying in a day. That can take on, so if you think of hours, we're measuring time. Time can take on for a number of hours, can take on any value between 0 hours and 24 hours in a day, right? You could have 3.5 hours if you studied for 3 hours, 30 minutes in one day, for example. So you can take on any value on that interval. So that's a continuous random variable. And then the normal distribution is a continuous probability distribution then, because it's the probability distribution for a continuous random variable. So remember, if it's a probability distribution, right, it's just giving us the value of every single possible value that the event can take on. So we're looking at every single possible probability for some random variable that's going to be normally distributed. So some properties of the normal distribution. So the normal distribution is a continuous probability distribution for some random variable. We're going to call this random variable x. Now again, remember, x is just a name. You can call it anything that you want to call it. It doesn't matter. But for our purposes, we're going to always call the normal distribution x. And again, it's the most important continuous probability distribution in statistics because so much stuff in the real world is normally distributed. Most everything you can think of is more than likely going to be normally distributed in some way. So for example, heights of people are normally distributed. Shoe sizes are normally distributed. Length of fish are normally distributed. So almost anything you can think of is probably going to be normally distributed. So it is the most important continuous probability distribution that's in the field of statistics and that we're going to study. And so the graph of a normal distribution is called the normal curve. It takes on, so the features of this normal curve, the mean, median, and mode are all going to be equal. So remember, this comes from the fact that this is a symmetric distribution, which is point number 2. So the normal curve is bell-shaped, symmetric about the mean. So remember what this means. Mean, median, and mode are all equal, and they're all in the middle, right? So mean, median, and mode all are right there together. So this is mu, but this can also be Q2 and the mode. So total area under the curve is equal to 1. Now you can use calculus to show this is true, but you don't have to. For the purposes of our class, you need to know that the total area is 1 because we're talking about a probability distribution. So the total probability, so area, think of area as synonymous with probability. So if the total area is 1, that means that all of the probability underneath this normal distribution has to add up to 1 just because it's a probability distribution. So the total probability is 1. That's why our total area under our curve is equal to 1. So the normal curve approaches, but it never touches the x-axis as it goes further and farther out from the mean. So as we go way out towards the ends out here, it's going to get closer and closer, but it's never going to touch. There's always still going to be some space between the x-axis and the curve. So in other words, there's always going to be some area out there, some probability out there, as far out as we can go, all the way from negative infinity to positive infinity. Between plus or minus 1 standard deviation away from the mean, so mu minus sigma and mu plus sigma. This is just another way of saying plus or minus 1 standard deviation from the mean. So looking at this region, our graph is going to be going upwards to the left. So it's curving up out here on the left-hand side and the right-hand side. So anything further out from plus or minus 1 standard deviation from the mean, the graph is going to be opening upward. Anything in between there, the graph's opening downwards. So because it's changing from opening up to opening down at those points, we call plus or minus 1 standard deviation away from the mean an inflection point. Again, this goes back to the calculus behind the math. You don't need to worry about it too much. Just know that plus or minus 1 standard deviation away from the mean is called an inflection point. That's really what you need to know. The main purposes for knowing that are they help you to sketch your normal curves correctly. So we have infinitely many normal distributions. We're not limited to just one, just like when we were talking about binomial back before spring break. We could have any number of binomial distributions depending on how many trials you were doing. So you can have infinitely many normal distributions based on its mean and standard deviation. So whatever the mean is, whatever the standard deviation is, that's going to create a unique normal distribution. So the mean tells us our middle. It tells us our line of symmetry. So your mean is always going to be in the middle. Standard deviation is still going to describe the spread of the data, so how the data goes out away from the mean. So whenever we look at these three normal distributions down here, notice the first two have mean equaling 3.5. So the A and B, the middle of those normal curves, are 3.5. But then the standard deviation is different. So what the mean tells you, that tells you where the middle of your normal curve is. Standard deviation tells you how big the spread of the data away from the mean is. So how far away those two inflection points are. In other words, so the bigger the standard deviation, so if we look at normal curve A, it has a standard deviation of 1.5. So what this means is our graph is going to spread out and open downwards plus or minus 1.5 away, so a total distance of 3 units away from the mean, considering both sides together. Our graph's going to be a little bit wider. So, and then if we look at graph B, our standard deviation is 0.7. So now we only have opening downward for 1.4 units. So our normal distribution is narrower. So the larger the standard deviation, the wider the graph. The smaller the standard deviation, the shorter the graph, or the taller and skinnier the graph. So it's not going to be as wide. So larger standard deviation, it's going to mean a shorter, fatter graph. Similarly, notice on graph C, the standard deviation is the same as it is for B. So it's 1.7, but our mean is different. So our mean is 1.5. So what that's done, it's shifted our middle of our graph down, but yet the width of it is going to be the same as graph B. So if we look at a couple of normal distributions, so of these two, curve A, curve B, which of these two curves has the greater mean? So remember, the mean, we're looking for the middle of the graph. So if we look, we can eyeball normal distribution B's means about 12. And normal distribution A, just go down from the middle to our x-axis, we're about 15. So because graph A's up here around 15, 15's bigger than 12, that means curve A has a larger mean. So curve A in this case has our larger mean. Now, same two normal distributions. Which of these two curves has the greater standard deviation? So remember, standard deviation, we're looking for our spread of the data, or the width. So how wide is it? So remember, the larger the standard deviation, the wider the graph. So if we look, graph A, just looking, the inflection points are somewhere, say around maybe 8 and 16. Graph B's inflection points, maybe somewhere around 14 and 17. So we can clearly tell looking at this that if we're looking at the width of the two graphs, graph B is clearly wider than graph A. So graph B has the larger standard deviation. So the wider the graph, the larger the standard deviation is.